Alright, FRQ number 1. So basically we kind of have like a yo-yo situation. So A wants us to use integral calculus to show that the moment of inertia is 1/2 mr squared. So we can do this. So we know I is going to be equal to integral r squared dm. Okay. Alright, let's go ahead and actually write out a couple of things that we know that will help us. So alright, and then we also know so dm is our mass, r is distance from center, dr is our thickness, and then we know that density equals mass over volume. And so for this, since we're integrating, we want the change in mass over the change in volume. And then we can go ahead and solve this. dm is going to be equal to m over v times dv. We're going to need that for this because we have here that moment of inertia for a cylinder is going to be integral r squared dm, and we use this because a cylinder is it is a three-dimensional object. So we can go ahead and use this that we just found and plug it in for dm. Alright, so now we pull these out, pull this out, m over v. Okay, so now with dv, it's almost like the change in volume. So what we want to do is we want to use the function or formula for volume of a cylinder. So h would be your height of the cylinder, and then you have 2 pi r, and then you also want to account for the thickness of the cylinder, so your dr. And then you're going to go ahead, I'm going to start writing a little bigger, and pull out things again. So that's going to be your height and your 2 pi. And then you're left with the integral. And so now you have your r squared times this r, so r cubed dr. Alright, so like we did with this v, we're going to plug in the formula for volume of a cylinder for this v. So that is time, however, it's going to be a little different because you're not accounting the change. So instead you just get that. And then you can cancel out. And then now we want to integrate R. Okay, so now we have this. We can go ahead and simplify this side. Oops. Okay, and you have to remember that when you integrate, the little cheat is you add one and then you divide it by whatever that number is. So in this case, it would be 4, and then you would be dividing by 4. So and then so remember you add 1, and then you divide by whatever number that is. And that is still R0. So that is going to be, you can kind of move things around, you know, you want to move the R's so that they're under each other. So you get 2 over 4 times R to the 4th over R squared, and you can pull out mass. And then with that, you get 1/2 m and then R squared. So that is how you get that using integral calculus. Alright, on to part B. And then, so this has 3 parts, so part BI. So the block is released from rest, string starts to unwind, causing the cylinder to rotate with the rod. Calculate the linear acceleration of the block. Alright, so what we can do is set up torque. We know that torque is equal to your F perpendicular times R, and is also equal to I alpha. So in this situation, our F perpendicular is going to be our T so on the side over here, we know, so in this, you have your F of G, and then your T. Okay, so we can use that because we can't just leave it as T, that won't get us anywhere. We need to get some sort of variables to help us move the problem along. So we need to solve for T in some sort of variable. So according to this, it would be mg minus T is equal to ma. And then you can go ahead and move it around, and you get mg minus ma is equal to T. Now this is helpful because now we can plug that into here. Mg minus ma times R equals I. So yeah, I omega. Alright, so now let's expand I. So we know I is 1/2 r squared, and then omega. Actually, it wants linear, so we should change this to a over r. And we do that because, if you remember, a equals r alpha. So when you move it around to solve for alpha, you get a over equals alpha. So that's why that is, alpha can go to that, and it wants linear acceleration, so that means we need to have a, and that's why we're changing it. So we can go ahead and cancel out r. So this would cancel out the square, and then those would cancel out. And then we can go ahead and simplify. Okay, from here, you want to get a and a together. So then that's ma plus ma. And then what you can do is you can pull out a. So then you get 1/2 m plus m. And then that makes it easier to solve for a, because then you can just divide. So then you just get mg over 1/2 m, big M, it's a little m. And so that is equal to a. So now we have that. So now we can go ahead and plug in our numbers. So m is, so this is, so mg is fg. So that's just the mass of the block times 9.8, and then 1/2, and then m of the cylinder, 2.5, plus 2, plus little m, mass of the block. So go ahead, plug this into calculator. Alright, so then you get and remember, acceleration is meters per second squared, and I wanted linear acceleration. Okay, so moving, okay, yeah, still filming. Moving on to part I. See, calculate the net torque. Alright, so you can just go ahead, set up torque, and that is, the quick way would be to do I alpha. So you can go ahead and plug in stuff that we know. So I is 1/2 m r squared. And again, we can use, so since we have linear acceleration, we can change it again into a over r. We can change alpha into a over r, excuse me. And then that way we have everything, we don't really need to convert on the side or anything, and we can just plug everything in. we can cancel out r in that case. Alright, so that gets us torque. Units for torque. Alright, moving on to part I. Grab another piece of paper. Okay, moving on to part I. Okay, so now it would like us to, let's see it, sorry, calculate tension. Alright, so we can go ahead and use this to calculate tension. Because we have everything that we need, so there's no need to go and find something on the side. We can just plug everything in as is. So we have to remember this is the mass of the block, not the cylinder. So 2.8 minus 2, and we found acceleration, remember? Alright, so that is the tension in the string. Okay, so that was part B. Now moving on to part C. So, on the axis below, sketch the angular momentum of the cylinder as a function of time from the moment the mass is released to shortly after TS. So let's go ahead and copy this graph as best as we can. Alright, so as you remember, linear momentum equals I omega. Now, we have to remember that this is essentially a constant. It's not going to change. However, our omega is changing because there is an acceleration, so it is going to increase. So that means in terms of L, so let's go ahead, kind of just write it without the I, because I doesn't do much except it gets multiplied to it, but it's just a constant. So if omega is increasing because there's an acceleration, that means L is also increasing because of acceleration. So it's going to increase. Now, it says here that at TS, that is when, so remember this is a yo-yo, so at TS, that's when the yo-yo is going to start going back up after it has fallen down. So what that means is, okay, so now now we're at TS, right? So we also have to remember that A is going to be constant because it wouldn't really make sense for a yo-yo to, when it gets to the bottom, it just stops. That doesn't really make that much sense, because the yo-yo is supposed to go up and down. So that means it also has to have enough acceleration for it to go back up the string. And so that means even after it has fully unraveled, it is still going to be, it is going to have that constant linear L. Alright, on to the last part, part D. Okay, so now instead of a solid cylinder, it is a hollow cylinder. Negligible friction, string is attached in the same place, the block is released from rest. So the time it takes is TH. Now, is the time TH greater than, less than, or equal to the time of TS? So we're looking at T solid versus T hollow. Okay, so I'm going to explain this as best as I can. So what's going to happen is the time for a hollow cylinder is going to be greater than the time of the solid cylinder. Now this is because of the moment of inertias. The moment of inertia for a hollow cylinder is greater as opposed to the solid cylinder. And what that means, and when you think about it, inertia is the resistance to change. So if you have a greater resistance to change, that means it's going to take longer for whatever is going to happen. So if a hollow cylinder is going to have a greater resistance to change as opposed to the solid one. So that means it's going to take a little more for the hollow one to unravel, as opposed to the solid one, which has a smaller resistance to change. So that means it's going to take a smaller amount of time for the cylinder to unravel. Okay, that concludes FRQ